previous class, we carefully looked at the definition of phase transitions. Okay. And we spent some time elaborating that. There is a very precise mathematical way in which phase transitions are defined. And I just gave you those definitions. And I asked you to check that if you take your one-dimensional Ising model case, where you had all the information, and you took those definitions, then you would not get any transition. Okay, in the one-dimensional Ising model case. So let me begin by asking if you have any doubts from the previous lecture. Any doubts from anyone?
Sir, I have a doubt. Sir,
yes.
The way we define phase transition, it was intrinsic to the Ising model case. But phase transition is a very common thing. It happens in gas, liquid phase transition.
No. Yeah. It's very common. Of course, we had to keep an example in mind, right? That's why I was telling you to focus on the Ising model all the time. But we talked about a very particular kind of a phase transition. Liquid gas does not fall into that class. The particular kind of phase transition we were talking about is one of the thermodynamic phases has a particular symmetry of the Hamiltonian, whereas the other phase does not have that symmetry of the Hamiltonian. So the liquid gas does not fall in that class of a phase transition. So we would not talk about that. But many phase transitions fall in that class. Solid to liquid falls in that class. Okay. Ferromagnet to paramagnet falls in that class. No, let me complete. So I'll hear you, but let me complete. So metal to superconductor falls in that class. So normal liquid to a superfluid falls in that class. Many of them fall in that class. So we were talking of that phase transition, those kinds of phase transitions. Okay, but you had some more things to say. So go on.
Sir, over here we have we take the limit n tending towards infinity, and then we take the limit h tending towards 0. So because we have a magnetic field in the system.
Okay. So yeah, so you must be confused about the notation. Yeah. So let me just say a couple of things again. If you're still confused, then tell me. Okay.
Fine, sir.
So suppose you have any general Hamiltonian. It might not be the Ising model. Okay. That general Hamiltonian is something like this. So whatever, it's some sum of whatever, many interactions, right? Something. So let's say J prime. Okay. Suppose you have a suspicion that there is a phase transition here, and the nature of the phase transition is, as I said, nature of the phase transition is that there is one phase where the symmetry is unbroken. So remember, we asked a question that is the symmetry broken, and that's a yes or no question.
It's a bit out of focus and unclear. Like
oh, I see. Let me try. Let me try how to do this. Okay, so I guess I'll. Sorry, this is worse. Is this better? This one? Oh no, this is worse. The chalk stroke is light. Well, I don't think so. I have been writing with chalks for 20 years and it's still the same. So, okay. Maybe
sir, in that case, a bit zoom in would be better because the strokes are actually apparently very light. So I guess.
Okay, it's the same stroke I have been using for 20 years. But anyway, sorry. Maybe today is an off day for me. But anyway, is this better? I'll zoom in a bit. Is this okay? Is this fine?
Yes, sir, fine.
Okay. Yeah. So, So now the point is that you remember from the previous class that in one of the phases, the paramagnetic phase, the symmetry of the Hamiltonian was preserved. And what is the symmetry we were talking about? This symmetry. Okay. This was preserved, which meant that this quantity is 0. Whereas in the ferromagnetic phase, this symmetry was broken, even though this is present in the Hamiltonian. Okay. Now, what is the formal way of thinking about it? You take any Hamiltonian. This may or may not be the Ising model. You take any Hamiltonian. This Hamiltonian is a sum of many terms like this. And then you remember I said to think of what the possible order parameter is. So you try to choose a quantity which very simply distinguishes between the symmetry unbroken and the symmetry broken phase. It should be some physical quantity or some physical correlation function. You call that quantity your order parameter. Oh, sorry, let me use some other notation here. So let's say I change this to J. This is your Hamiltonian. Now, this is your original Hamiltonian. This is the physical Hamiltonian. Whereas here, I just say I put an extra term, H times O. Okay, this I just do by hand. So this H times O, you see, now I have changed the problem. I have modified the problem. This O is my proposed order parameter. And this H is just a field which is coupling linearly to that proposed order parameter. For the case of the Ising model, this H has a physical interpretation of a magnetic field. There may be cases where there is no such physical interpretation. That is okay. I am not worried about that. After that, in this new theory, so to indicate that this is a new theory, I put this subscript here. In this new theory, you calculate this expectation value. Of course, this expectation value is non-zero. Why? Because you have explicitly put a term like this, and so you have removed the symmetry, right? By putting this term like this. It's like in the Ising model, if you put a magnetic field, you have, of course, removed this symmetry, right? The up-down symmetry of the spin, right? This symmetry. This, you have removed this symmetry. So this is obviously non-zero, but now comes the important point. You calculate this quantity, okay, for a fixed N and a fixed H at a given temperature. This you can do. This is a well-defined problem, even though this is different from your original problem. Now you do the following. Now you take the limit, N tending to infinity first, and then you take the limit of H tending to 0, and you calculate what happens to this function. This is some well-defined function. If this function goes to a non-zero value in this sequence of limit, then you land up here. Whereas if the limit becomes 0, you land up here. Is this clear? This is a general definition. Okay.
Yes, sir. Now it's clear. Now it's clear.
Okay, very good. So this is a very general and a powerful definition, even though this is slightly abstract, but this is the proper way of defining phase transitions. Okay, good. Okay, so today, let me try to motivate to you from some simpler arguments why you should not expect a phase transition in the one-dimensional Ising model, whereas you should expect a phase transition in the two-dimensional Ising model. Okay, that's the first thing that we'll try to do. Then after we do that, we'll move to something called the mean field theory. Okay, later on. And after we are done with the mean field theory, we'll try to calculate the exact transition temperature for the two-dimensional Ising model. Okay, and maybe tomorrow or day after, I would prepare again a handwritten set of notes on the Ising model, and I'll upload it. And then you can download it from Google Drives. Okay, so right. Okay, So this is the rough plan. So let's start with why there is no phase transition in one dimension. Okay, so let's see. So now I'll introduce the one-dimensional Ising model again. And tell you why there is no phase transition. So while arguing for that, what will play a very key role is the free energy of the theory. Okay, because we are at finite temperature now. So what will play a crucial role is the free energy of the theory. So yeah, so let's take the Ising model. So of course, the Ising model at t equal to 0, the 1D Ising model at t equal to 0 can have two ground states. So one ground state is of course all the spins being +1 and so on. So actually the +1s, let me indicate by the sign plus, okay, because it'll help me later on. So this is one possible ground state. Let's imagine a huge lattice and this is one possible ground state. The other possible ground state is minus, all of the spins being minus, okay? So let me consider this ground state. Okay. So now comes the first point. The first point is that, of course, at finite temperature, when I calculate free energy, the expression of free energy is this. Therefore, I need to even think of the entropy. See, of course, the energy is minimized by this term, but of course, there is only one such guy here, which is all plus. So the entropy, which is log of the number of microstates, is just 0. I mean, if I tell you that all the spins are plus, there is a unique state you can draw, right? So at finite temperature, it's not obvious that this will help with the free energy, even though it helps with the energy. So then the question is, what else can you do? So now what you can do is try to build a domain wall. So what is a domain wall? So let's see. So let me keep all of these plus, and let me just choose a side. Maybe I choose this side, this particular side. Okay. And after this side, I keep everything to be minus. Okay. So the picture sort of looks like this. If you sort of look at the domain wall, all of these guys are plus, and then suddenly these guys turn minus. Okay. So now let us try to see what is the free energy change from this reference configuration. So free energy change is delta E minus T delta S, right? By definition. So what is delta E? This is of course the ground state. So it can have the minimum possible energy, right? What is the E final minus E initial here? So this, can somebody tell me? So let's say your Hamiltonian is again SI plus 1, right? Let's say on a periodic boundary condition with a large system size. Okay. So what is the delta E that I should consider here? Just compare this spin configuration and this spin configuration. What is the energy change?
Sir, I have a doubt.
You have a doubt. You have a
Yes.
doubt in my question.
No, sir, not in question. One thing that, sir, why are we considering that all the plus pins is actually the ground state of the system?
Sorry, why is it not the ground state of the system? Because Oh, okay, okay. Maybe I did not make it clearly, mention it clearly. Let's put a minus sign here, right? And let's say J is equal to 0. Oh, sorry, J is greater than 0. Is this okay? Do you agree that this is the ground state of the system?
Yes, sir, but then again, minus all the minus won't be the ground state, right?
Won't be the ground state or will be the ground state? Sorry, will be the ground state or won't be the ground state?
Yes, sir, will be the ground state. Put a
Okay,
ground
so
state.
yeah, I'm saying this is also a ground state,
Okay.
this is also a ground state. Look
Okay,
here.
fine.
Okay, so now that your doubt is clear, can you answer my doubt? What is delta E? Just compare this state and this state. What is delta E? Of course, it's some positive number. So what is it?
2 times the flipping of
2 times what?
the energy needed for
No. Look. Please don't give such answers, right? I mean, look, you guys are grown up. Here is an equation. I'm asking you a precise question. Just give the answer in terms of the parameters defined in the Hamiltonian, right? You cannot give me an answer like 2 times whatever the energy, whatever. This is not an essay competition, right? Just tell me the answer.
2
2F.
times F.
What is F?
F into S.
No, what is F?
Square.
What is F? See, look. What is F? In this equation, there is no F, right?
Sir, the change in energy will be J.
No, that's not correct. What is delta E again? You're missing some factor.
So what is the expression for H?
Look here. Look, this.
So that is minus F sum over.
What is
SI,
F? Sorry, wait. What is F? What is F here? Do you see any F? This is J. This is J.
Oh, achha.
By the way, no. Look. Okay, this is J, right? This is not F. Okay, I didn't know my handwriting was so bad, but okay. This is J. Okay.
Sir,
So 2 times J.
Okay, yeah. 2 times J. That's correct. So this is 2 times J. Now comes this more interesting thing. What is this? What is this guy? This is more interesting. What is this guy? How would you answer this question? See, when I say that my energy is my ground state energy, then either I have this configuration or I have this configuration. Let me just take this configuration, right? Now, if I say that my energy is not exactly the ground state energy, it's 2 times J plus the ground state energy, then of course there are actually many configurations which have this exact energy, 2 times J plus the ground state energy. And of course, how would you think of those configurations? You see, I chose to put my minus spins after this point, right? At this point, all the things here are minus. But I could have chosen this guy here, right? Still, I would have gotten exactly this energy difference, right? So, for example, if I drew this configuration on a very big lattice, I would still have gotten the same amount of energy, 2J. So what do you think is the entropy of these kind of states? So there are many such states which are consistent with this energy. So what do you think is the entropy of these kind of states? Let's say there is a big system with capital L spins. So what do you think is the entropy? Remember, entropy is related to the log of the number of microstates that is allowed with some constraints.
So minus K n into n minus 1.
Minus T times, okay, yeah, okay. So something like this, right? That's what you're saying. Sorry, I said L spins, so maybe, okay, let's put N spins, so yeah. Something like this, right? Is this fine with everyone?
So n into n minus.
No, not n into n minus 1. N, log of n. Because you see, I just need to set the location of this boundary. And there are basically n ways of doing that. This boundary could have been here, but similarly, this boundary could have been here, and so on. Okay.
There is no end of that boundary. Oh, okay.
No. You can consider the end of the bound. No, sorry. No, maybe I'm confusing you. This is not such a hard thing. Think of this here. So, okay, I understand what you're saying. You're saying what happens here, right? But you see, that is fixed. I mean, if I choose this guy, I have already told you that all the spins here are negative, right? So if I've chosen this guy, anyway, this configuration is set. You don't have any freedom here, right? So the only choice I have to make is where is the initial location of this guy.
Okay? Sir, I guess it should be n plus 1, ln n plus 1.
Okay, it doesn't matter for n being large, it doesn't matter, whatever it is. So n plus 1 is the same as n.
That's for sure, but normal combinatorics says that it should be n plus 1.
Okay, if you're happy with n plus 1, it's fine. I don't care about it when n is large. Okay, now comes a slightly more interesting thing. Suppose instead of one domain wall, I put two domain walls in a very big system again. And of course, again, I have a reasonable amount of freedom in choosing these two things. Then, can somebody tell me what is delta F again? Firstly, what is this term? 2j is not 2j anymore. It should be some higher number. So what is that number? See, the logic is very simple. When you look at the increase in energy, the increases in energy is only due to this bond and due to this bond. Right? The rest of the bonds still have the energy to be as low as possible.
So 4j is delta E.
Yeah, 4j. Now, what about the entropy?
So T K V ln n into n minus 1. That
correct. Something like that, right? So something like that. Yeah. Actually, n times n minus 1 by 2. Okay. So yeah.
Yes.
Okay. Right. Okay. So now you see, all of you guys immediately notice one very interesting thing. What is that? At any finite temperature, the free energy of a one domain thing is lower than the ground state. Why? Because no matter how small the temperature, if this n is a large enough number, then this negative quantity would dominate over this positive quantity. Okay. So no matter how small your temperature is, if my system size is big enough, ultimately this negative number would dominate over this positive number, right? Similarly, if you have two domain walls, then of course, again, this negative number would dominate over this positive number. Is that clear to everyone? Just from the equations, right? No matter how small your temperature is, this factor, if your n is big enough, would always dominate this factor. Okay. So the basic idea is that once you take your system to finite temperature, there are all kinds of these domain walls with just one step like this, domain walls with two steps like this, 3 steps and so on, right? And they'll entirely dominate the free energy of your theory, and they'll just kill this order. Okay, that's the rough idea. And the reason they dominate the free energy is because this energy cost in creating one domain wall or two domain walls does not depend on the system size. There is no system size dependence here, right? Neither in 2J nor in 4J. There's no system size here. But the entropy depends on the system size. Here, right? So the entropy always dominates in one dimension for this kind of a model. So this is the rough idea. Let me do a more precise calculation for you. Okay, but is this rough idea clear to you all? That just because you need to minimize free energy at any finite non-zero temperature, what is going to happen is you will get all kinds of domain walls, which are of course absent at zero temperature. At zero temperature, this term is not present. But at any finite temperature, you will get all kinds of domain walls and they'll just destroy this order. Okay, that's what happens in one dimension. So yeah, I'll now do a slightly more systematic calculation based on this idea, but this is the rough idea.
Sir, why this does not happen in the 2D case?
In what? Say that again, please. Why?
Why this does not happen in the 2D case?
Okay, we'll come to that, but let's first do the 1D case. Okay, there is a crucial difference in 2D, and the crucial difference which we'll come to hopefully in today's lecture is that this energy factor would also start depending on the system dimension. That will be the crucial difference. Okay. In 1D, it does not. In 1D, it does not. Because, this wall is like a point here. So in 1D, it does not. So it does not care about the system size. Okay. Good. So let me just do a slightly more formal calculation, just going by this idea. You already understand the one domain wall case and the two domain wall case. Now, let me go to the case of capital M domain walls. Okay, capital M domain walls. So what does that mean? You just count the number of these things. Okay. So in this case, this is M equal to 2 in a very big system size, right? If you draw one more, that's M equal to 3, right? And so on, right? And the rule is very simple. The rule is,
Sir,
yeah.
could you
Go on.
please once again explain that why delta S for the two boundaries says log of n into n minus 1 by 2?
Oh, because all that you need to choose is the location of the first wall and the location of the second wall. The first wall can be chosen in n sides. The second can be chosen in n minus 1 sides. And of course, whether you choose the first wall and the second wall, it's indistinguishable. So it's n times n minus 1 by 2. Basically, C choose n2. You understand, right? It's just this.
Okay.
Yeah, it's just this. Yeah. Okay. So, so if you have M domain walls, basically that just means that you have something like this. Let's say M equal to 3, right? Something like this. Sorry. Like this. So what that means is very simple. You just keep drawing pluses. Once you hit a wall, you just flip the sign. This is minus. Again, you hit a wall, you flip the sign. This is plus. Again, you flip the sign. That's it. So this is your spin configuration. Right? Okay. Now, let us consider the case where there are capital M domain walls. Capital M domain walls. So if you have capital M domain walls, then the delta F can be written like this. So let me just write an expression. Minus, this is of course C choose M, like this. This is the expression. Here I have made an approximation. So the approximation is that these walls are not extremely close to each other. If they are extremely close to each other, this expression of energy would change. You can think about it, okay, when you go home. you can think about, oh, sorry, maybe you're already at home. But anyway, after the lecture, you can think about it. So, yeah. But if the walls are reasonably far apart, okay, so let me just explain this here. This is not so difficult. So suppose you create something like this. Then, of course, you know that the energy of this guy is 2J, right? However, suppose you create something like this. Where these two domain walls are extremely close to each other, just one spacing apart. Then the energy is not 4J, okay? Well, actually, in this case, it is 4J. Let's see. So you have broken this bond and you have broken this bond. Okay, so let's see how much energy you have. So your delta E is due to this bond and this bond. So it's again 4J. Okay, that is fine. So it's still 4J. Okay, but then there must be some case where it's not 4J. Let's see. Let me try to see if I can find some case where it's not 4J. So I break one bond. Okay, this is not immediately clear to me. Maybe you guys can think about it. Are there configurations of M domain walls where the energy is different from this quantity? Okay. If the domain walls are reasonably far apart, then of course this equation is always true. Okay. But you can try to think of counter examples. But in any case, if the domains are far apart, then this equation is completely true, and this equation is also true. The way you count domain walls. Okay. One problem with this part again is if the two domain walls are very close, then there are some conditions such that this domain and this domain cannot touch each other and things like that. Then that brings some complications even in this factor. But again, if the domains are far apart, then it doesn't matter. Okay. What that simply means is that M divided by N is a reasonably small number. Okay. That's the condition of being far apart. It's a reasonably small number. Then I can write this equation. Okay. I don't have any problems in writing this equation. Just by repeating the argument of one domain wall, two domain wall, three domain wall. The question for you to think about is, how does this argument fail if there are many, many domain walls which start coming close to each other? Okay. So, yeah. I'm getting slightly confused now, but you can think about it later. Okay, good. So this is the thing when you have capital N domain walls and they are sufficiently far apart. Now, what we'll need to do is we'll just need to use the approximation that factorial is basically n times log n minus n when n is large. When n is large. Okay. So we'll just use this approximation. We'll assume n is large and m is large, and we'll assume that this ratio is small, and we'll give a name to this ratio. We'll call it x. Okay. So I'll just use this formula now, and I'll use this extra symbol here, and I'll just write down the free energy. Okay. So let me just write it down. So I'll skip a few steps of algebra, but please verify this algebra at home. So basically this expression, after using this and using this symbol, basically boils down to the following. So I can pull out the n, 2 times Jx plus temperature. I think I have also, okay, sorry. So here I should have written a KB, but somehow let me assume that I'm doing everything in units of KB equal to 1. Okay, so you can reinstate KB in your notes by just dimensional arguments. Okay, so yeah. This is the full answer. This is the full answer when I have this approximation for a situation where I have capital M domain walls. Okay. Now, suppose I tell you that I have given you a fixed temperature. Can you tell me what this number X is? How will you attempt to solve this problem? So this is an expression for a general X, right? For the free energy. But suppose I tell you that at a finite temperature, I need to determine what is the average number of domain walls at that temperature, right? Then how would you do that? See, at 0 temperature, this number is 0. The density of domain walls is 0. At very high temperature, this number is rather large. Okay, it should be close to 1 at very high temperature. Okay, because at very high temperature, 2 neighboring spins are independent of each other. So you can have you will have a huge number of domain walls. Okay, so this number X starts from 0 and goes to a large finite number at T tending to infinity. So if you're at a non-zero temperature, it's reasonable to assume that this X is some small number, right? If your temperature is very low, it's reasonable to assume X is some small number. In fact, then this approximation works. Okay, but the key question I'm asking you is, how do you determine this X from this equation? I've given you an equation. How do you determine X from this equation? Any ideas? The hint is that this is the change in free energy. So you need to, of course, do something with the change in free energy, right? So can you see what to do with this thing? Okay, I mean, suppose you choose, yeah, that is correct. So what should I do? This is a function of X. What should I do? What operation should I do to determine the correct value of X at a given temperature? So you mean I take a derivative of delta F with respect to X and set it to 0? Yeah, so that's correct. That's how you find the X at a given temperature. So if you do that, that's absolutely right. All that you need to do is you need to extremize the free energy with respect to X. Once you solve that, then you get the following equation. Just verify that you get this equation. Now let me put the KBT back, because I had put KB equal to 1 here. Let me put it back, which actually means that X is 1 divided by e to the 2j divided by KBT plus 1. In fact, I can ignore this plus 1 at low temperature. Why? Because this factor is a rather large number at low temperature. So let me ignore this plus 1. Okay. So what is this thing? This X tells you the average distance between domains, right? This X is the average distance between domains. Why? Because this X is related to how many domains you have, right? If this M is very small, that means that the average distance between the domains is large, obviously, right? So this X which is just m divided by n, is related to the average spacing between two domain walls, right? At a fixed temperature. In fact, if you want to think of the average correlation length, which is again dictated by the average distance between two domain walls. Actually, you guys did not catch me here. By the way, I said one thing incorrectly. If this x is small, is the distance between the domain walls large or small? The distance between the domain walls is large, right? Right, exactly. So if you want to associate a correlation length from this x, basically you need to take the inverse of this, right? So basically, if you want to set a correlation length, that should be x inverse, okay? Because the average distance between the domains is related to x inverse, okay? This x is related to the density of the domain walls in the system. Therefore, the distance between two domain walls is related to x inverse. And this quantity is just from this expression, e to the 2j by kbt. So this again tells you how to derive the correlation length of the Ising model at low temperature. Remember, we talked of this when we did the exact solution, that the correlation length goes like this. It's exponentially large. This is the expression. And this is the physical mechanism by which this happens. At any finite temperature, what happens is that there is a small but non-zero density of domain walls in the system. As you raise the temperature, this density also increases. And this non-zero density actually induces a finite correlation length in the system and destroys this magnetization. Okay, so that is the physical mechanism through which the one-dimensional Ising model loses its magnetization immediately at finite temperature. Okay, the key ingredient here is that the energy of the domains does not depend on the system size. Okay, I just say that there are 3 domains here, and from that I just say that the energy is 3 times 2j, which is 6j. There is no system size dependence here. There is no system size dependence here. However, the entropy depends on it, because the entropy would then be this guy. And of course, this depends on the number of spins that you have. So at any temperature, at any non-zero temperature, the entropy of these domain walls dominate, and they are enough to kill the order which is present only at 0 temperature. Okay, this is what happens for the 1D Ising model. Now, why is the 2-dimensional Ising model completely different? That's the question. Okay, so now I'll draw a small picture on the board, which will exhaust all my artistic skills, and then I'll explain to you. Okay, so, but this is the logic for the one-dimensional Ising model. This argument is quite nice because just from the simple argument, which is of course true at low temperature, we could even derive the correlation length. And now you can sort of see physically one way to interpret this correlation length at low temperature. At low temperature, at least for the 1D Ising model, the correlation length is related to the average distance between two domain walls. Okay. At finite temperature, see, this domain wall can fluctuate, this domain wall can fluctuate, this can fluctuate, right? But there is still a well-defined notion of an average distance between two domain walls. This distance, this is like an average distance. That distance is related to the correlation length, like this. Okay. So,
Sir, how did we discuss his transition here?
how did we? What? How did we?
Does it give any information about phase transition in the system?
Okay, yeah, it does. So see, of course, the strict way of saying that there is no phase transition is that earlier definition which I discussed, right? Where you take the limits. That's the strict way of thinking about phase transition. This is a heuristic way. This is a heuristic way to show that the one-dimensional Ising model does not have a phase transition. Why is that? The reason is that, okay, so at any non-zero temperature, see, this is the reason. Let me try to draw a picture and motivate this to you. Suppose you draw a big lattice and then you draw lots of domain walls in that lattice like this. So let's correct for the domain walls. And so on. Suppose you think of this spin and this spin. Let's call this spin I. Let's call this spin J. And let's say I want to compute Si, Sj. Let's say I want to compute this object. What does this object depend on? This object just depends on the number of, what is it? The number of domain walls you have crossed. In this case, you have crossed 1, 2, 3, 4 domain walls. Okay. So basically, this expression is -1 raised to the power m. Let's see why this is true. Let's see why this is true. In any given microstate. Let's see why this is true. So just look at this case where you have crossed 4 domain walls. 1, 2, 3, 4. Once you cross the first domain wall, you know that the rest of the spins are negative. Then you cross the second guy, they are positive. Then you cross the third guy, they are negative. Then you cross the fourth guy, they are positive. So necessarily this spin and this spin have the same sign. Either they are both plus together or they are both minus together. And therefore this is true. Suppose I bring another domain wall here. Let me just do it here. So let's say this guy. See this, what I'm doing, right? Suppose I do this. Then what happens? Then you immediately see that this is minus, minus, minus again. So you see how this equation comes, right? So this is clear to everyone. Is this clear to everyone? M is just the number of domains here. So this is by definition. So given any microstate, you can always write this microstate in this domain wall language. And then by definition, if I choose two sides I and J, so let's say this side is J, I just count the number of domain walls between sides I and J for that microstate. Then I can write this expression for Si times Sj. This is the expression. Okay. This is part 1. I'll go to the next thing now. But is this much clear to everyone?
Sir, you are taking one spin initial, the left spin from the leftmost domain and the right spin from the rightmost.
No. You don't even need to do it on the leftmost or the rightmost. I am saying just take any spin here, fixed spin, and take any fixed spin here. Just count the number of domains between these two spins. There may be domains here. I don't care, right? For this argument, I just need to count the number of domains between these two spins. Okay?
Sir, can you once again say the argument behind this? Like why we are writing it like that?
No, I mean, how do I show this more clearly? I mean, the definition of a domain is that the spins to the left of the domain are plus and the spins to the right of the domain are minus. So suppose you have one domain here, right? Then it's clear that if you choose any two spins on one side of the domain wall, then SISJ is +1. Whereas if you choose any two spins on two different sides of the domain wall, SISJ is -1, right? So here I just motivated with a picture that SISJ is in general -1 raised to the power n. Okay. Now comes the very important point. This M is finite at any finite temperature. In fact, this M is proportional to n. I proved this at any finite temperature. right? Why? Because we got a non-zero x here from our calculation of m by n. We got a non-zero x. That means that this m is an extensive quantity. We just calculated the average of this, right? But of course, it's an extensive quantity and it fluctuates. So you see what you're doing for a very large system. You are basically, when you're doing this average, you are taking -1 raised to a large number, and then of course that large number is also fluctuating. So basically, it's highly plausible that you will just get 0 at the end of it, because this is a highly fluctuating quantity when m is large. Okay, it's not that m is 1 or 2 or 3. M is some large number and it's fluctuating around that large number, right? It has some well-defined average, but it's fluctuating around that large number. And basically, if you take the expectation value of this, you will get 0. That's how the magnetization is lost in the one-dimensionalizing model.
Sir, if you want to find out the average, we will do SI, SJ, P.
No, sorry.
probably-
Average of what? Average of what? Which quantity?
Average SI, SJ.
Yeah, so if you want to find the average, by definition, it's -1 raised to the power m, by definition. Yeah. Now what do you want to say?
Sir, I was saying that. Sir, I was saying that if we want to do the average at some particular temperature, then
Yeah.
we will have then there is no fluctuation in m.
No, that's not correct. No. See, remember, don't get confused. See, when you were doing StatMech, if you refer to my previous notes as well, everything fluctuates at thermal equilibrium. It's just that you are calculating an average or a second movement or a third movement, that you can write things like that. But more generally, things have a distribution. In the previous calculation, we just computed average of m. Okay, we just computed average of m. That does not mean that m is that fixed number at a particular t. That just means that, if you look at the number of domain walls or whatever, if you look at this m, right, at a fixed temperature, then this m sort of fluctuates like this with a well-defined average. This is what it means.
No, sir, I was referring to the formula that we just derived for x.
But look, that formula is for the expectation value of m. Yeah. See, that's why all these concepts are important. Remember, how did we derive that formula? We extremized the free energy. But please refer to my previous notes. There is a complete section which tells you that the fluctuations of any thermodynamic quantity or a density is dictated by the second derivative of the entropy. So if you take higher expansions, then you would get these fluctuations as well. Am I
Yes,
making
sir,
any sense?
I understand the point.
Okay, fine. Yeah. See, I mean, this is very, very important, right? I mean, see, most often in thermodynamics, we calculate the average because that's the simplest quantity to calculate. That does not mean that quantity is fixed to that number. Okay, that never means that. Okay. So, in fact, those fluctuations about that average actually give you 0 here. Okay. So, right. Anyway, so just think about this at home. I mean, this is an indirect argument. This is not a very simple argument. I mean, the simple argument is you just use transfer matrices, calculate your answer, and take the limits, and then you know that there are no phase transitions. But this is a very, if you wish, a very interesting and a physical argument, which tells you how at finite temperature domain walls destroy the phase transition. Because you already know one thing, that this m is a large number. It's proportional to n, the number of spins in your system. Now, usually, when you have -1 raised to a large number, and the number can fluctuate, usually when you average that quantity, that goes to 0. Okay, because, I mean, just think about it, right? If you do this game, then almost with equal probability, you will get -1 and +1. Because sometimes this m would be even and sometimes this m would be odd. And basically you'll get an equal probability of these two things in this case. Okay, and that's how you get a 0 here. Okay, at finite temperature. See, now see the beautiful thing. At 0 temperature, we know that this m is precisely 0. That's the beauty of this argument. We know that at 0 temperature, this m is precisely 0. That's why at 0 temperature, you get +1 for this quantity. Okay. But at any non-zero temperature, we know that this m moves from 0 to some x times n. Okay. So immediately it goes from 0 to a very big number. Okay, which is actually an extensive number. So this is what happens. Okay. So yeah. Okay. So now let me go to the two-dimensionalizing model case and again draw a domain wall for you. I'll just draw a single domain wall for you, and then you will understand the difference between 1D and 2D. Okay. Okay, so now let's go to the two-dimensionalizing model. So let me draw this picture for you. Remember the 1D picture. In the 1D picture, this is what was happening for a single domain ball. The energy was just 2J. It did not depend on how big the system was. That was the crucial bit for the one-dimensionalizing model. Now let's look at the two-dimensionalizing model. So let's try to draw a domain. So why don't I do something? I just mark a region. Maybe this. Sorry, of course, this picture is not very good, but I think you get the idea, right? Yeah, sorry. This is the idea. So let me draw the broken bonds here. Now what? Something like this. Yeah. So I don't know. Is it clear what the domain is here? So there are all these negative spins here in some region, in some closed region, and the neighborhood of that is a positive spin. All positive spins. So if you wish, there's some region I have marked out. All the spins inside this region are negative. All the spins outside this region are positive. And of course, the energy of the domain is coming because of the bonds at the boundaries which are broken. That's why the energy difference is coming. Maybe this is a better picture than this, but is this clear? Yes, no.
Bonds are broken in a sense.
Sorry, what? Say that again.
What did you mean when you said bonds are broken around the domain?
Yeah, what I meant was that, see, in the ground state, all the spins are, let's say, positive. That's my choice. So let's say all the spins are positive, like this. Like this. Okay. Now remember, the Hamiltonian of the Ising model for 2D can be written as a sum over nearest neighbors SISJ, right? So given this spin, I can think of the energy living in these bonds, right? Because literally I'm calculating this bond, I'm calculating some other bond, and I'm just summing all those answers, right?
Yeah.
So when the system is at its ground state, each of these bonds also have the minimum possible energy.
Right.
Okay.
Yeah. Okay.
Now you see, in the interior of this region, the spin is minus minus. That is also the minimum possible energy of the bond. The only problem is in these shared regions where the bonds are broken, in the sense that they have a higher energy than the ground
Yeah,
state.
energy is high. Okay.
Yeah. So that's it. This is a pictorial way of thinking about it. So, okay. So can somebody see the crucial difference? Now I'm drawing a domain. And suppose this domain has a perimeter of L. This domain has a perimeter of L. Okay, that's sort of the length of the domain. Then without worrying too much about factors, can somebody tell me what is this delta E in this case? Earlier it was 2J, right? In the 1D case, it was 2J. Now in this case, what is this? Is it 2J times something?
Times L, I guess.
Exactly, 2J times L. That's the crucial difference. In general, this answer is 2J L raised to the power D minus 1. In 1D, D is 1. So 1 minus 1 is 0. That's why this thing did not depend on the system size. But in 2D, it's 2 minus 1, which is L. So this is what you get. Okay. So of course, the system realizes if a domain is very big or very small. That's the crucial bit. Okay. Because of course, if the perimeter is large, you pay a higher energy cost. If the perimeter is small, you pay a smaller energy cost. Now comes the second thing. You need to estimate the entropy. So this is this, roughly. This is not an exact calculation, roughly. So how do I motivate that? So remember, I need to sort of break small l number of bonds to get this much energy, right? So if you wish, small l is the number of broken bonds here, which is related to the perimeter of this domain. So now the question is, how do I sort of choose a closed curve with these small l number of sticks, if you wish, right? Because of course I need to close this curve. There's an interior and an exterior, right? So I just need to solve that problem. So of course that's simple. This is a square lattice. Suppose I choose my first stick here, right? Of course, there were 4 ways of choosing this guy, right? I could have chosen it here, here, here. I choose it here to lay on this point, right? Then the second stick, there's still some freedom. I could choose it here, here, or here. Let's say I choose it here. Similarly, for the third stick also, there's some freedom, right? And so on. So if you just think about this problem of making a sort of a closed region like this, if you think about how many ways you can do it, the answer is C raised to the power small l. This C is very hard to calculate. This is a non-trivial calculation, how to calculate C. But the important thing is that the answer is some number raised to the power L. That is easy to understand because you see each stick you can place in, so sort of you do a small calculation here. Maybe you take 10 sticks, L equal to 10, right? So for the first stick, there are sort of 3 ways of doing it. In fact, 4 ways of doing it. Then for the next stick, there are 3 ways of doing it. Then for the next stick, there are 2 ways of doing it. Then you go here, Then there is again 1, 2, 3 ways of doing it. So you're multiplying all these non-trivial numbers, right? And you're multiplying these numbers sort of L times, right? Sometimes this number is 3, sometimes it's 4, sometimes it's 2. That depends on what the shape you're growing. Okay, because if you have placed a stick somewhere, you cannot place that stick again there. That's my rule. But nonetheless, whatever this number is, it's growing like this, c raised to the power L. Okay, so that much is clear because I'm taking all these numbers and I'm multiplying them, and that's the rule. So if I draw all kinds of polygons, then I'll have this structure by definition. Okay. Okay, this is slightly complicated. Counting is never sort of easy to convey. You think about this argument, but this is okay. I'm saying that calculating this C is very difficult. That I agree. If you want to solve this counting problem, okay. But understanding that the number of ways in which you can draw such a closed region, given sort of L bonds or sticks on the square lattice, that is growing like this. That is not so hard to understand. But I mean, this is a counting problem. Each of you would have your own way of thinking about it. So you think about it. Okay. So now look at the very crucial thing that has happened. Delta E is 2J times L. T delta S is T times log of CL, which is T times small l times log of C. So now you see that something very remarkable has happened if you calculate the free energy. So the free energy looks like this. Sorry, log C. The free energy looks like this. Can someone see any crucial difference between the 1D and the 2D case? Sorry, I mean, maybe this is still not clear to some of you how this happens. But I mean, I have given you one argument. Now you go back and think about it. If it's not clear, maybe we can discuss it at some point. But what I'm trying to say is that calculating the C is very, very difficult. But understanding that the structure of this counting gives you a C raised to the L is not so difficult. Okay. So, yeah. Okay. So I get this answer. Now, can somebody see something very different in 2 dimensions?
Both the terms increases with L linearly. Over there,
yeah. That is one thing. Yes, that is one thing. So both the terms increase with the perimeter in the same way. In 1 dimension, that was not true. Term scaled as L to the 0, whereas the second term sort of scaled as log of L. Okay, so that was one crucial difference in 1 dimension. In 2 dimensions, both the terms scale in the same manner. That is correct. Both of them scale proportional to L, which is the length of this perimeter. But there's another very crucial difference. Can you notice that? See, as you know, in thermodynamics, you want to minimize free energy. So can you notice some very crucial difference which depends on the temperature? See, the C is some number, which is some fixed number. It's some geometric property. I'm telling you it's hard to calculate, but it's some number greater than 1. I don't know what that number is. That's some complicated thing to calculate. But it's some fixed number. Okay, so fixed quantity. This is some fixed quantity. Now can you tell
me? As we move from 0 absolute temperature,
sorry, can one person say at a time?
Sir, if we go above absolute 0 temperature, as we move from T equal to 0 to increasing values, at 0 T, 2JL del F is 2JL, and then if we very small increase in T does not like make it negative. So when we go above the T, the delta F is actually positive.
Correct, correct. So that means that the formation of domains is thermodynamically penalized. Okay, there can still be small domains in your system because, of course, the probability of a domain is related to this quantity. Okay. So there can of course be small domains. So in the case when delta F is positive, there is a probability of small domains. Okay, but the domains cannot become too big. Okay. However, when the temperature, so there is a critical temperature from here. So this is of course not the exact critical temperature. This is still an approximate calculation. So you just equate log of C times T star to this guy. So this is log of C, this guy. When the temperature is below this number, it's actually unfavorable to create domains. However, when the temperature is above this number, then you see again something similar to 1D happens, right? Then it's very, very, very favorable to create domains, and again you destroy order. But the very interesting thing is it happens at a finite non-zero temperature. It does not happen at an arbitrarily small temperature. So that is the difference between 1D and 2D. So all the difference was created from the fact that in energy of the domain is related to the perimeter of the domain. Okay. Whereas in 1D, of course, it's just a point. In 2D, it's a sort of a surface like this, right? So the energy also knows about how big or small the domain is. That was the crucial thing. So, yeah. So basically, if your temperature is very small, you will have small domains in your system just because of the Boltzmann factor, but they won't kill your order. They'll just decrease the average magnetization from being 1, which it is at 0 temperature. Let's say all the spins are plus, 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 plus. So the average magnetization decreases from 1 to maybe 0.98. Then you raise the temperature a bit more. Maybe that 0.98 decreases to 0.8. And to go to 0. Once you cross this in the system from small domains to big domains, and then they kill the magnetic order, just like in one dimension. Okay, so that's the crucial difference between 2D and 1D. In 1D, this process happens immediately at any finite temperature, whereas in 2D, you need to crank up the temperature to some non-zero value before which this process starts to happen. That all kinds of domains are possible. Okay, so maybe it's a good point to stop here today, and later on in the next class, I'll introduce something called mean field theory. Then we'll come back to these questions again. Okay, so any questions on this? Yeah, this is a bit subtle. You need to think about it. But what I wanted to highlight was that the key difference between one-dimensional Ising model and two-dimensional Ising model is this fact, that in 2 dimensions, the energy depends on the perimeter for a domain configuration, whereas in 1 dimension, it just depends on this point. That's it. That creates a crucial difference in the interplay of energy and entropy. Okay, that's why you get completely different behavior in 1D versus 2D. Okay. So, right. So, any questions? Maybe you can think about it, and in the next class, you can ask me questions. Yeah, if there are any immediate questions, you can ask me. Okay, maybe not. Then let me sort of erase this and yeah. Okay, so that's it for today then. So yeah, if you don't have any questions,